So first, just a quick little overview of absolute value inequalities. Because what you'll find is that these are very easy examples and they make a lot of sense. And when the problems get jazzed up, you can just fall back on these easy ideas and it all falls from here. So if you're looking for values of x such that the absolute value is greater than or equal to 3, well, 3 is greater than or equal to 3, the absolute value of 4 is greater than or equal to 3, the absolute value of 5, and so on. 3.1, 3.2, all of this stuff, right, would make that equation true. But then also, since it's an absolute value, the absolute value of negative 3 is equal to 3. The absolute value of negative 4 is 4, which is greater than or equal to 3. And so all of this negative stuff works too. So you see we have these two distinct regions, right, where that make this true. And so that's why they call this sometimes the great or, right? Either the x really is greater than or equal to 3, or the x is less than or equal to negative 3. And so that is your answer for this, for greater than problems. And notice on this one, it makes perfect sense from the picture, but notice that both the inequality and the sign of the original guy end up swapping. And when the problems get bigger, the only thing that happens is that inside changes, and you'll just have a little bit more to solve after you set up these two equations. Check. So that's how you deal with a great or, right? Either the x really is greater than or equal to 3, or the x is less than or equal to negative 3. And anything you need to do from there. Oops. And then this one, I meant to make it a less than. So now if you're looking for x's that are less than or equal to 3, well, clearly things that are less than 3 work, but only up until a point, because the absolute value of negative 4 is 4, which is bigger than 3, right? So you have to stop at the negative 3, because as soon as you get to like negative 3.1, the absolute value of negative 3.1 is positive 3.1, and that's no longer less than or equal to 3. So when you're less than, you've got this one region in between. And you could break it up into cases, but faster, I just like saying, well, that x is sandwiched between the negative 3 and the 3. It's always less than signs, and it makes a lot of sense. It's negative 3 is less than or equal to the x's, which are less than or equal to the positive 3. The x is sandwiched between those. So I call this a less than sandwich. And so when the problems get tougher, you start off with the same setup, except this inside is funkier. And we'll see that soon. But every weird problem is going to stem from these two ideas, which make a whole lot of sense when you just think about what x's make that true. So we'll see how that works. All right, so the first one you have for us is a doozy, but it's no different than what we said we were going to do. So if we see a less than, and I see a less than and the absolute value is all alone, I'm going to go ahead and make this less than sandwich. I'm going to say that this inside part, this x plus h squared minus x squared, is going to be sandwiched between a positive 3h squared and a negative 3h squared. And then I just have to solve whatever comes out of this. So I'm going to keep cleaning this inside. So this x plus h squared is x plus h times x plus h. So that's x squared plus xh plus another xh plus h squared. And then I'll just bring down that minus x squared, and I'll bring down the rest. And I'm just going to keep cleaning up this middle. So the x squareds go away. That's pretty nice. And then I've got 2xh plus h squared is less than 3h squared. And then I'm just going to keep trying to solve for x. So I am going to subtract h squared from my three-sided equation. And so I'm going to get negative 4h squared is less than 2xh is less than 2h squared. And then I'm going to keep solving for x. X is being multiplied by a 2 and an h, so I'm going to go ahead and divide by 2 and h. Now this is why, at this point here, it was so important that they told us that h is greater than 0. Because with inequalities, you basically treat them like equations, but if you ever divide by a negative, these inequality signs would have to flip. But since they're ensuring us that the h is greater than 0, we don't have to flip the inequality signs. So we can keep going. So divide by that, I'll get negative 2h, and is less than x, which is less than h. And so that is your answer. Excellent. Yeah, so it was a mess, but if you can do that, you can do anything, right? For part B, I believe the only difference was that h was less than 0. So for part B, if h is less than 0, then these inequality signs would flip. So you'd have negative 2h is greater than x is greater than h, because you're dividing by a negative and then everything is backwards in the negatives. So you can keep your answer like this, or usually I like the less than, so I'm going to reverse it, that h is less than x is less than negative 2h. And that hideous thing is your answer. And sorry it's in such big font. I made a tough looking problem look like kindergarten writing. So there you go. So here we go again. I see a less than. So I'm going to make a less than sandwich. So this middle part here, this x plus 1 over 2 minus x minus 1 over 3, needs to be between 1 and negative 1. It's trapped between there, just like a basic little x is less than or equal to negative 1. That inside's got to be between there and there. And so now I just got to clean up this three-sided beast. So I got to make a common denominator for the inside, so a nice, or I'm safe actually to multiply every single piece by 6, because 6 is nice and positive. I'm not going to be flipping around any inequality signs, so this will be okay. So this will be negative 6. It'll distribute to this guy, and so 6 divided by 2 is 3, so it'll be 3 times x plus 1. And then minus 6 divided by 3 is 2, so it'll be 2 times x minus 1. And then I'll make that less than 6. And you could also grab a common denominator and then multiply by 6. Either way, you'll end up here. And then you just keep cleaning. Distribute minus 2x plus the 2. Make sure that negative distributes. And keep cleaning the inside, or the middle. So this is x plus 5 is less than 6. And then just keep solving for x. So subtract 5 from every single side. So you'll have negative 11 is less than x is less than 1. And that is your answer. Sometimes they'll write it in interval notation that the x's start at negative 11 but you don't equal to it. And then you go to 1 but you don't equal that. So if they want it in interval notation, you'd leave it there. So again, I see a less than, so I know that this inside part must be trapped between 4 and negative 4. So I make my little less than sandwich, and I keep going from here. So multiply everybody by a 3. So negative 12 is less than x minus 2 is less than 12. And then add 2 to every single side. So you get negative 10 is less than x is less than 14. If they want it in interval notation, the x's start at negative 10 and they stop at 14. We can't equal either because it doesn't have the equal to sign, so parentheses, there's interval notation. Okay, so if I'm reading this problem right as like three separate problems, A, B, and C, part A doesn't have any absolute values, so you just solve like normal, subtract the A from both sides, and then to get the x alone, you got to divide everybody by a -1. When you divide by a negative, the sign's going to flop, and you'll get a nice and positive x, a negative c, and a positive a. And so this is your answer in that form. If you wanted interval notation, I suppose you could say you start at -c plus a, and you keep going until infinity. Check. For B, we've got our absolute value signs. We see the less than, so we set ourselves up a little less than sandwich. So we take that middle part and we trap it between the c and the -c. And then we just keep solving for x like normal. So I'll subtract a from every single side. So I'll get -c minus a is less than -x is less than c minus a. Phew. And then I'll divide everybody by a -1 to get this x alone. When I divide by a negative, the signs are going to flop, and I'll get a nice and positive x in the middle. When I divide this side by a negative, all the signs are going to switch, so it'll be positive c plus a is greater than x is greater than -c plus a. And so this is your answer. I kind of like it better with less than, so I'm going to just turn it all around. I'm going to start with this side and say that the -c plus a is less than the x is less than the a plus c. I kind of like that better. And interval notation would just be that your x's start with the smallest, -c plus a, and stop at the biggest, a plus c. Phew. And then this last one, part C, is a greater than, which we haven't done in a while, and we just set that up as a big, great or. So instead of having a less than sandwich, we're going to have two equations. One, that a minus x really is greater than or equal to c, or maybe a minus x is less than or equal to a -c. Awesome. And then we just keep solving each of these two problems for the price of one. So subtract the a over, c minus a. Divide by -1, so the inequality flips, -c plus a. So there's one answer. And then we go to the other one, subtract the a, -c minus a, divide by a negative, so the inequality flips, and you'll get positive c plus a. So slap an or in the middle, and that is the answer to your greater than problem. If you wanted to write it in interval notation, you've got x's that are less than or equal to c plus a, or x's that are greater than or equal to c plus a. So your x's start at -infinity. So like this region starts at -infinity and goes until c plus a, and we'll unite that with this region that starts at c plus a and goes to infinity. And I forgot that since I have the equal to sign, I can now use brackets to represent that I can equal these last values. But the infinities will always have parentheses because you can never equal infinity.